So first, I'd like to thank the organizers for the opportunity of presenting this work here today, and I'm really happy about this workshop. I think it's the first time that I see the discussions that we are seeing here, and I think this is very important. So I think it's more than time to start talking about these things that we are talking here. So I think this is really important. I'm very grateful for this. So we're talking about this work, which is a collaboration with the group of Antonio Assin in ICFO in Barcelona. And I'm now based in the Universidade Federal de Pernambuco in Recife, also here in Brazil. And what we did here, we are proposing a new correlation measure to identify non-Markovianity, okay? So thinking about the scenario that I'll be talking, I'm talking about the dynamics of open quantum systems. So I have a system of interest that is in contact with some environment. And I think this is interesting because, okay, just from a fundamental point of view, but not only this, we know that all the coherence effects, they come from this unavoidable interaction of system and environment. And if we are able to understand this interaction better, maybe we can do some engineering in the environment in order to fight against these effects. But also, we, as I will show you, we have some dynamics, like some non-Markovian dynamics, where it can be that you are losing information to the environment, but at some point we will start to recover this information. So we want also to explore this type of dynamics. So I think everybody knows this here, but we will be talking about maps because we are talking about dynamics. So we want this quantity to be completely positive and trace preserving in order that I'm guaranteed that I'm taking density matrices to take density matrices. And how we will define if the dynamics is Markovian or non-Markovian. Well, let's just go back to what is the classical definition of Markovianity. So if we go to a stochastic process where I have a random variable x, which can takes value xn and at time tn, we say that the dynamics is Markovian if the conditional probability satisfies this condition here. Which means if I want to know what's the probability that x takes the value xn, I just need the probability that the probability that x took the value x n minus 1 and this conditional probability. So I don't need all the what happens, the whole history, what happened before the time n minus 1. So then here I have this idea that, okay, the future evolution just depends on the present state. I don't need like x0, what happens in 0, whatever, 1, 2. And if this condition is not satisfied, then I have a non-Markovian dynamics, and then I would really need all the history to talk, okay, if I have this present state, what will happen in the next step? This is exactly what happened in the random walk. So if the probability that I will go to the right or the left, it doesn't depend what happened before, okay? Then we just want to keep the same idea, but now look into quantum dynamics. So I will be talking about maps. And I want to define this Markovian or non-Markovian, look into the maps. So I say that the dynamics is Markovian if the map can be divisible into other CPTP maps. And then here I recover again this idea. So if I know the state in time s, so if I know rho s, I can say what is the state in time s plus t. I don't need anything about the time 0. To know the state in time 0 to know what will happen in time t plus s, okay? So if this divisible condition is not satisfied, then I know I have a non-Markovian dynamics and I need the whole story to say what will happen in time t plus s. Great, so this, as I said, this non-Markovian dynamics sometimes is identified as this backflow of information. So system is losing information to the environment, but at some point it can recover, or as a non-monotonic decay of information. And there are many quantities where you can see this recover. The two most common ones, one is distinguishability. So if you look to the distinguishability of two states, thinking about a qubit Bloch sphere. So I start with two orthogonal states, and then they start to evolve and I'm losing distinguishability, I really like to talk with my hands. I hate when we have these microphones in conference. But okay, I'm already getting used to it. I feel like trapped. And so you start to lose distinguishability, but it can be that at some point you recover this distinguishability again, okay? And another witness of a non-Markovian dynamics will be entanglement. So you have your system that is contact with the environment, entangled with an ancilla, and then you can start like in time zero, you start with some maximally entangled state, and then you start to lose entanglement. But then at some point you can see a recover of entanglement, and this will be a sign of non-Markovian dynamics. So if the dynamics is Markovian, it will necessarily always decay with time, but it can be that you also have a non-Markovian dynamics and you are just here in this green line, okay? So this is a trace that you are sure you have a non-Markovian dynamics, but it can be that you have a non-Markovian dynamics and you won't be able to identify it with entanglement. And then when I started to work with open quantum system dynamics, I was asking myself, well, is there any quantitative that I will always see a recover of this quantitative in a non-Markovian dynamics? And yes, there is. So there is this result from Francesco Buscemi and Nadja where they show there is an equivalence between divisibility and monotonic decrease of information classical and quantum stochastic process. So what they are doing here, they are exploring this old result where we have that a quantum evolution is Markovian if and only if you look to the trace norm of this Hermitian operator, okay, it has to decrease. And this has to be true for for any Hermitian operator, okay? So which means that if you have a non-Markovian dynamics, there should be at least one Hermitian operator where this trace norm doesn't decrease. And what they identify is that all Hermitian operators can be written in this way. So rho 1 and rho 2 here are density operators, and P is just a probability. And then they saw that this theorem can be related to another problem, which is what is the average probability to correctly identify a state extracted from an ensemble of two states, maximizing over all possible measurements. So imagine the game is like this. I'm preparing a quantum system, and we know before that, okay, I just have these two possibilities, rho 1 and rho 2, and then I send to you this quantum system, and you have to guess if I have prepared rho 1 or rho 2. And you have just one measurement. It can be anything, a POVM, whatever, okay? But you just have one try. You do a measurement and you say, okay, Nadja, it was rho 1, or no, it was rho 2. The best that you can do will be to have this, or like on average, if you will do this game many times, we will get the best probability of guessing, which is related to this trace norm of this Hermitian operator that can be constructed from this ensemble of states. And P will be the probability that rho 1 is appearing or rho 2 is appearing, okay? So we see, if this trace norm is decreasing for Markovian dynamics, then the probability, the guessing probability will also always decrease for Markovian dynamics, which means that if I have a non-Markovian dynamics, I can come with at least one ensemble of states where I will see an increase in the guessing probability. So they know what is like, they are proposing a quantity that will always increase. At least you know that you have at least one ensemble where this quantity will increase for non-Markovian dynamics. Great, but the problem is here they show this result, but they don't tell you how to construct this ensemble, so you don't know. You know that there is an ensemble, but you don't know which ensemble is this. So they don't give you any receipt how to find this ensemble, and also not to how to find the optimization in the measurement, which is even more like hard in thinking about what is the dimension of your space. So it's a nice result, but it's kind of frustrating because you know that you have it, but sometimes you don't know how to find it. And another thing that, like, when I saw this result, I wasn't really totally convinced. Is that, well, if I want really to convince people that these non-Markovian dynamics, they are useful thinking about quantum information processing, is that, okay, usually we are used to tell about these things, okay, when we want really to say this is something useful for quantum information processing, we are used to talk about correlations, not guessing probabilities. Although, okay, some of you will know some protocols where you will like have an advantage when you have an increase in the guessing probability. But when we are talking, most of the times we're talking about entanglement or whatever, mutual information, we are not really talking about guessing probabilities. So I was still asking myself, is there any correlation measure that will always detect non-Markovianity? And this really trying to find, like, can I really say that these non-Markovian dynamics are like a resource for quantum information processing? And then we thought, okay, let's check what is this measure, what we want this measure to satisfy. So we want a measure to be, okay, it has to be bigger than 0, where 0 will be when I have a product state. And I also think it's reasonable that this measure is non-increasing under local operations. So if I just don't have correlation, I don't want that with local operations I will create correlation, okay? I think this is reasonable. But then you can say, okay, Nadja, this is just entanglement, mutual information. Yes, it's true. They are all correlation measures. They satisfy these conditions. But the problem is, as I already said, they are like measures that we know already. They don't identify non-Markovianity always for all maps. So the first example here, think about I start with a state that has some entanglement, and then the first step, I have some entanglement breaking channel. So, and this is true, like if I start with any state with entanglement, I guarantee that I'm going from this entanglement set to a separable set, okay? And then what happens in the second step from time, so I'm going from time 0 to S, and then from time S to T, I have a positive map. So in a way that the combination of these two guys, okay, this is something I changed the notation here, and I didn't define it before. Now I noticed this, sorry. Before I said just about the divisibility, and here I'm using V because this is I'm considering here non-Markovian dynamics, which means the intermediate map is not a CP map. Okay, so I'm not satisfied. That's why I'm using this V. Like this is not really a physical process. Okay, but just if I try, like if I force to have this divisibility, I would find this map, which is this. In this case, I'm just using a positive map, which is something that will not be happening in the lab. Okay, but then what I say is that, okay, I start with entanglement state, and I go to the separable set, and then it can be that this positive map happen, and then I just stay here. I won't be creating entanglement from this state here, okay? And then I just stay in the separable set. So this is an example of non-Markovian dynamics where I won't be able to identify using entanglement. The entanglement is just decreasing, okay? And then we went to mutual information. We thought, okay, maybe entanglement is not our the measure that we are looking for, but maybe mutual information will do the job. And then, okay, we had some dynamics and some numerical evidence where we couldn't see a recovery of mutual information. But then we are also a little bit worried, like people could always ask, yeah, but maybe it's your numerical simulation, the way that you're searching for these states, and then you're just failing to find that maybe the set is so small that you cannot find this recovery of mutual information. And we wanted to have some analytical example. So we got an analytical example, but it's very non-trivial, so I decided not to present it here, but I'm just telling you, we have an example where we are sure that there isn't any recovery of mutual information, okay? So the two typical, the usual suspects, like entanglement and mutual information, they won't witness non-Markovianity. And then we thought, okay, I think we should have to come with some new proposals, like some new correlation measure. And then we went back to De Francesco's paper, and we thought, okay, let's get inspired by his idea, and let's see if we can come with a correlation, with a measure that satisfies these three conditions that I presented before. And what we are using here is that we are using this idea of maximally entropic POVMs. So the scenario is the following. I have a bipartite state, and then I'm doing some measurement on part A, and I'm preparing then part B, okay? And I'm doing this like as general as I can, so I have these POVMs. So one element of the POVM is preparing B in one of the states. So at the end, I have an ensemble of row Bs, and each one appearing with probability Pi. And I say that these POVMs, they are maximally entropic if these probabilities are the same. So like each outcome has the same probability of occurrence. Okay, so I have different, it can be that I have different row Bs, but they will appear with the same probability. And then I will go back to this guessing probability. So I haven't defined before the guessing probability, but this given an ensemble of states, the guessing probability is the average probability to correctly identify a state, maximize overall possible measurements, okay? And then if I just have two states and which are appearing with the same probability, we can show that this guessing probability is related to the trace norm of this difference, or this is also, we know that this is the distinguishability, okay? And the way that we would define then the correlation measure is we are maximizing this guessing probability, but we are just constrained to the maximum entropic POVMs. So, okay, we are not just looking to all set of measurements that we can do, but we are constrained to the maximum entropic POVMs. So we are guaranteeing that our ensemble is, although the states that they are appearing in the ensemble, they have the same probability. And in this way, why we are doing this? Because if we define like this quantity satisfies all these properties. So, and then we can call it a correlation measure, okay? But not only this, okay, what is the really behind here? What is this quantity is identifying? So it's identifying the most distinguishable ensemble of an ensemble that I'm preparing where the states will appear with same probability. So, okay, so imagine that I have this bipartite state. I want to prepare an ensemble of one of the parts, and I want to do it in a way that I have one of the parts. All the states, they are preparing with the same probability, and now I want to get the most distinguishable ensemble. And this is what this quantity is quantifying. We can see, okay, people always look me a little bit puzzled when I get to this part of the talk. I will just give an example of what happened with what is this quantity for a product state, and then I think I will convince you that this is really a correlation measure. So I'm really measuring if I have correlation or not. So let's look here. If I have a product state and I'm doing some measurement on part A, what happens is that, okay, it doesn't matter. It's just that I'm always preparing the same state on part B, okay? Because it's a product state. Part B, it's not, there isn't any correlation with part A, so what is happening there in A, it doesn't matter for B, okay? And then in this case, the probability is the same, so it's always appearing row B, row B, row B. And then we now thinking about this game only with two possibilities. If the same game again, I'm preparing, I have this ensemble. So, but now row 1 and row 2 are equal to row B. And then I send it to you. What's the best that you can do to say, she prepared row 1, or no, she prepared row B? What would you do? Yeah, you just guess. Flip a coin, whatever. And then the best that you can do will be, your guessing probability will be 1/2. So if I just randomly say, oh, row 1, it was row 1, row 2, row 1, row 2, at the end we will have 1/2, okay? And then going back here, oops, yeah. Then I will, that's why this minus 1/2 is appearing in fact, because I want to have it 0 in 0. So then what I see is that, okay, if I just have a product state, the correlation is giving 0. And I really will need correlation here to start this quantity to start to increase, okay? So I'm really, it's not only a strange measure that I'm proposing just to satisfy the conditions that I want, but it's really something that is related to correlation. It's not straightforward, for me also not. Like when I looked it for the first time, I was like, oh, I don't like this. But okay, I have to accept. And when I started to present this work, now like I'm more convinced that this is really a correlation measure, and well, and that it's a nice result. So I'm not presenting we also have all the proofs that is non-increasing. Something that I haven't said is that we have two parties here, A and B, and we want it, so we don't have any preference what is A, what is B. So it can be that A is your system of interest, B is then CELA, and it can be I don't know, one is evolving, the other not, or both of them are evolving. So that's why we kept this maximum. So they are the two possibilities. If I'm doing the measurement, your POVM, you're applying on A or you're applying on B, okay? And I don't want to go through these proofs. I think this is not really useful. I think it's more like if you are interested, we can talk about it later. But what I want to tell you still is that, well, I'm telling you all these things, and I tried to convince you that the Francesco's paper, well, like it was a nice result, but it wasn't really practical. And now I want also to convince you that this result is more practical what we have in Buscemi's paper. And the idea is, okay, I told you I have a quantity that will always identify non-Markovianity. But now I want to convince you that I know how to find this ensemble of states in order to have this quantity, okay? Not only that I have this quantity, the correlation measure, but I know how to construct this ensemble, and then we will be able to see this increase in the correlation measurement. And then what we were exploring, it was another result from Bogna, Marcus, and Tony, which are also in this work here, where they show if they have a non-Markovian, and here there is some restriction. They are looking only to bijective maps. They can show that if you have this non-Markovian dynamics, then necessarily they know how to construct this ensemble of two states in order to see always an increase in the distinguishability, okay? So they know how to do it. And then we will be exploring this. So now, oops, our B part, okay, I will just do it keeping the POVM here on A, but I could do also in different ways. But our B part will be now the system and some other ancilla, and A is also an ancilla. And I will start then preparing my state, A, S, and A prime, with this, okay, these parts are the states that I know that they will show this increase in the trace norm. And the A part will be kind of a flag state, okay? And the POVMs that I will be doing, these two guys here. And what I'm doing, okay, at the end, I'm preparing the ensemble of states, which are these two states here. So they are related to the guys that I know already they show a recover in the distinguishability. And then how I relate this, how is the correlation measure of these two guys? So if I just calculate this guessing probability, and here I'm using this maximum entropic POVM, so they are appearing, these two states are appearing with the same probability. So we can calculate this, and then we will see that the correlation measurement is related to this trace norm. And then we just see that, okay, this trace norm is related to the original one, and we know already that this trace norm will increase for a non-Markovian dynamics, okay? So these two things are connected, so if the trace norm is increasing, the correlation measure is also increasing. So we know how to construct the states, and not only this, we are also, a trace norm is a problem that can be done with a semi-definite problem. It's a semi-definite problem, so you can calculate it efficiently. So we know how to construct the states, and you can calculate the correlation measure efficiently. So then I think this is like good points for this measure, okay? So then just concluding, we have discussed that entanglement multiple information failed to witness all non-Markovian dynamics. We proposed a correlation measure that's a witness of non-Markovianity in the extended setting for all evolutions that are bijective or pointwise non-bijective. So We don't have, in general, we still don't, we couldn't prove this for non-bijective maps. Well, there is always this discussion with non-bijective maps. Non-bijective maps is the map that they are not invertible. If they are physical, what's the meaning of non-bijective maps? But okay, this is another discussion. And, oops, spoiler. And I showed you that for a given dynamics, we described how states, how can we construct these states that give this recover of the correlation measure, and you show how you can evaluate it efficiently, okay? Yeah, and now I just want to make an announcement before I finish. Well, I don't know, some of you know already this event, which is a school and a workshop, 1 week school and 1 week workshop. It will happen next year in Paraty, which is close to Rio de Janeiro, here in Brazil. It's a very nice place. Some of you were already there, so please ask them. And yeah, check, we still, the website is on, but we still have to put more information there. But okay, the lectures are already there, so if you are interested, just check for the website. But I think it's a really nice event. And we are also worried about doing things in a different way and discussing also the different things. I think, I don't know, maybe if you're here, it will be nice to be there also. I don't know. Okay, that's all. Thanks.
Okay, questions?
So you talk about that entanglement and mutual information. They are not good measures for non-Markovianity. But is it that...
They are not general, like they won't identify all non-Markovian dynamics. It's not that they are not good.
But when they detect, it means that it's non-Markovian.
Yes.
Ah, okay, that was my... Okay, thanks.
They are just not general enough.
Other questions?
So maybe just following Gloss's question. So in your case, you were actually searching for a specific ensemble that shows these non-Markovianities, right? So for the entanglement measure or for the mutual information measurement measure, couldn't you also find, like, so that you fix the dynamics, but you change the ensemble such that it actually shows some recovery?
Yeah, okay. This is a good point that I wasn't clear, but it depends. If you fix the dimension and if you are allowed just one ancilla, then we are sure that the entanglement and mutual information, there are some dynamics where they will fail to identify non-Markovian dynamics. But if you are allowing to have more ancillas with more dimensions, then I don't know. I don't have this answer. This is something also we were thinking about. Like, but here we are in the same, like we are comparing same things. So just one ancilla with the same dimension. But if you can have more ancillas, maybe you will be able also to identify, okay? And especially for mutual information, we have the feeling that we have to investigate more in this direction, okay?
More questions? So if not, let's thank Nadja.